Hello, and welcome to Introduction to CFD. This is Architectural and MEP, Part 3 of a 3-part series. My name is Robert Smith, Solution Consultant for D3 Technologies. I support our sales team in their efforts to find solutions that make sense for our customers. I also support our customers after the sales process with training and mentoring, as well as project consulting. I specialize in the Autodesk Simulation products, including CFD and Inventor Nastran. I also work with Inventor and Vault. This series is intended to introduce you to the CFD technology. If you've never heard of CFD or how it is used in industry, this is a great place to start. Each part of the series will be targeted at one of the major industries where CFD is used: industrial flow control, electronics cooling, and architectural and MEP. This is by no means an exhaustive list. If you are in another manufacturing sector, such as vehicle design, for example, I expect that you'll still walk away from this presentation with a solid understanding of what CFD is, and we can help you dial in exactly how it might apply to you and your designs once you contact us for more information. In this presentation, we will start with a high-level overview of CFD. We'll discuss what CFD is. CFD is just one of many methods of computer simulation, and so we will discuss computer simulations in general, why we simulate, and when simulation should be done. D3 Technologies is an Autodesk partner, and so we use Autodesk products for simulation. The focus of this presentation is the CFD process in general. However, we will spend some time talking about where the Autodesk simulation products fit in the marketplace and who typically uses them. We'll then discuss how CFD works, what we can do with the results that come out of CFD, and what impact those results can have on a design. And of course, we'll discuss how you'll get more information about CFD and how D3 Technologies can help you. So, what is CFD? CFD, or computational fluid dynamics, studies the flow of liquids and gases in and around solid objects. Thermal effects can also be modeled. CFD is a method of calculation. Although it's not exclusively done with computer software, hand calculations using CFD are academic exercises. In real life, it's not practical to perform CFD without computers. So typically when CFD is discussed, it's assumed that a software package is being used. CFD is basically a method of predicting the flow behavior of fluids as they interact with solid objects. Heat transfer and its effects on the flow is commonly modeled as well. The flow can be internal flow, meaning it's contained by the solid object, or external flow, meaning it goes around the solid object. CFD is a method of computer simulation. Why simulate? Simulation leads to more efficient and better performing building projects in less time and at lower costs. It provides a preview of the performance of the design. Costs can be reduced as rework due to underperformance is decreased. Less rework also reduces the time needed to test and commission the projects. Requests for quotes can be returned quickly and with more confidence that your design will perform. Win more business. Let's compare the traditional design process with the design process that utilizes simulation. In the traditional design process, the initial concept is developed using a combination of past experience, hand calculations, and educated guesses. Using this method, projects often fail to meet performance criteria during testing. This results in the need for another iteration of the process, which means more design time and more construction. Each iteration of this loop adds cost to the project and increases the time it takes to get to commission and handover. When a design does pass testing, there's little confidence that the design is optimized. It did not fail, but is it over-designed? In contrast, manufacturers can use simulation, or virtual testing, to eliminate failed designs before construction. Initial concepts may fail to meet requirements, but iterating digitally is far less time-consuming and costly than iterating physically. In fact, iterating the design is so efficient with computer simulation that the designer can afford to continue iterating, even when a design has passed, in the search for a design that not only works, but is of the highest quality and lowest cost. New innovations can take shape, and more efficient designs are the result. All of this before construction begins. Innovation may be the greatest benefit that comes from digital simulation. Avoiding mistakes is important. Lowering costs will help you win more business, but ultimately, It's new ideas that differentiate you from the competition. Why do we want to innovate? That may seem like a question that does not need an answer. Of course, innovation is good, right? Try putting it into words, though. The reasons for spending time and money developing new ideas is different for everyone. Why are new ideas important in your industry? I encourage you to think about that while I cover a few of the innovation drivers we see in industry. Today we'll look at efficiency, primarily reducing energy use, which reduces operating costs and environmental impact. Quality and safety, which kind of bleed together. Occupant comfort is important, but controlling contaminants, pollution, and smoke from fires is often even more important. Efficiency means meeting air quality and thermal criteria using as little energy as possible. We've all been in spaces where airflow and temperature are not optimal. Uneven temperatures and stagnant air impact our comfort in a space. This is not a trivial issue, as occupant comfort impacts the performance and health of employees or residents. It impacts whether or not paying guests will return. Often, efforts to correct non-optimized flow will fix one problem but create another. We've all experienced rooms that are too hot or too cold because controls are monitoring another area with completely different thermal loads. Non-optimized flow not only creates poor air quality, but often cooling and heating equipment is consuming unnecessarily high energy to try and mitigate the problems in the design. Correctly optimized airflow helps designers size equipment correctly, place inlets and outlets correctly, and design efficient zoning and controls. Non-standard spaces are particularly challenging. Our textbook formulas, spreadsheets, and online calculators aren't always well suited for the spaces we're tasked with conditioning. CFD helps us predict the airflow and heat transfer in rooms with unusual shapes, sizes, and layouts. Effects such as solar radiation coming through large windows can be modeled in 3D. Real local temperatures and humidity on surfaces, air temperature, and human comfort can be quantified and visualized. Some of the innovation, driven by the need for energy savings, is in taking advantage of the natural properties of air to aid in heating and cooling our building with less added mechanical energy. Some of the most efficient types of ventilation systems have leveraged natural, displacement, and stack design concepts. If the air circulates on its own, then you can ventilate spaces effectively with much smaller air handlers and less ductwork. The challenge with these types of systems is to validate your innovation. Hot and cold air collection systems are very custom to the architectural design of the building. There's often a trade-off between form and function that has to be studied and optimized early in the project to ensure success. If you have never done it before and have to get it right the first time, then CFD is a must-have and one of the first things you should do. These types of buildings used to be only implemented by large companies and for flagship projects, but now it has become the targeted growth market for medium and even small firms. Here's some specific examples of this. The BWI pedestrian connector, seen here on the left, is a long space with an unusual ceiling and shape. There's a lot of glass. CFD was used to assess the comfort within the occupied volume, which is around 6 feet above floor level. The area between the air inlet vents and the ceiling is designed to create a stratification layer and effectively act as an insulating barrier. The glass wall is naturally exposed to solar radiation, and the challenge was to cause the air to flow in a laminar fashion such that it would not disturb the stratification layer and then wash over the glass wall to absorb the heat during the day and also reduce the buildup of condensation on cold days and nights. To achieve this, slot diffusers were required, but the HVAC provider had never implemented floor slot diffusers in this way and for a glass wall of this height. They were naturally very concerned that additional ceiling diffusing would be needed, but that was aesthetically not an option. Over a period of several weeks, 40 different variations were simulated, and an ideal configuration was selected. Without CFD, specifically Autodesk CFD in these cases, this would not have been possible. On a larger scale, the Singapore University of Technology and Design had the very ambitious goal of having a net zero campus. Understanding the correct orientation was key to achieving maximum natural ventilation. This not only helps prevent stagnation, but also reduces the carbon footprint that would have to be offset. It's not unusual for architects and designers to find themselves at odds. The architect has the artistic vision, and the engineers have to make it work. Understanding how these spaces will perform is key to reducing the necessary compromises between form and function. Data centers are not concerned with looks. Their challenges are managing the immense amounts of heat generated by the servers. This is an example of a case where human comfort is less of a priority than machine comfort. Humans may have a narrow window of comfort, but some machines like high-performance computers or precision machine tools have an even narrower window of operation. Thermal problems can reduce machine life and accuracy. Enormous energy requirements put even more pressure on operators to maximize efficiency. Often, data center operators are tasked with adding more and more machines into fixed footprints. CFD helps designers experiment with server and cooler unit placement to achieve this without enlarging the space or the HVAC equipment. As I stated earlier, air quality and safety often go hand in hand. Air quality may mean supplying adequate fresh air into a system and maintaining comfortable temperature and humidity. It's also about controlling the contents of the air, whether that be oxygen, a virus, a toxic fume, or smoke from a fire. Simulating the velocity, pressure, humidity of the air, while accounting for all heat sources and heat sinks, allows us to accurately predict the comfort of occupants. Knowing how long the air spends inside the space helps us to avoid stagnation zones that may have inadequate fresh air or uneven temperatures. Simulating different times of day and different times of year ensures our spaces are always comfortable and healthy. They can be measured empty or at maximum capacity. There's some very specific outputs available from CFD related to the comfort of its occupants, such as predicted mean vote and percent persons dissatisfied. Biological and chemical contaminants are always present, but controlling the contaminant exposure of occupants, surfaces, and equipment is the goal, with varying tolerance levels depending on the space. Tracking where air has been and where it is going is extremely important to medical facilities and clean rooms. They're concerned with the velocity of air near surfaces that may be contaminated, which may cause larger particles to become airborne. They want to know where a particle goes once it is airborne. Does it land on a clean surface? Or is it carried away to the floor or a collection system? Stagnation zones become a concern here as well, not just for medical spaces, but public spaces like hotels and schools. Good air circulation reduces the concentration of airborne biological contaminants that get us sick. This is obviously a very high priority today. Emissions and pollution can come from inside a building or from outside. Tracking where it goes is vital to maintaining air quality and safety. Proper placement of building air intakes requires understanding how toxic fumes and particles travel from their source and diffuse into the environment. In this example, the exhaust from a helicopter landing pad is tracked as it leaves the helicopter and is propelled into the surrounding environment by the rotor blades and the wind from the city. This helped predict the levels of pollution that entered the building intakes, but also how quickly the pollution diffused and how it impacts surrounding buildings. CFD allows us to simulate the interaction of multiple fluids with different properties as they move and diffuse. In a word, mixing. This also allows us to simulate the propagation and density of smoke as it moves and diffuses in a space. This allows us to determine visibility at any given time and location, so we'll be able to tell how long exit signs will be visible in the event of a fire. So, when is the best time to simulate and optimize your design? Over the project lifecycle, the ability to affect the functional capabilities of the design declines as the cost of making changes increases. The best time to identify performance or compliance shortcomings is during the design and engineering phase. This way, the design is still flexible enough to make the necessary changes, and the costs of these changes are minimized. Simulation is a key part of manufacturing today, but it'll be absolutely essential in the near future. We at D3 Technologies partner with Autodesk because Autodesk is looking forward, beyond the needs of industry today. We aim to prepare our customers to thrive in what Autodesk is calling the future of making. As I stated earlier, this presentation is not specific to Autodesk products. It's a generic look at the process of CFD and how it is applied, no matter what software package you're using. However, these software packages vary greatly in their capability and complexity. If you're watching this, you're likely new to CFD and just getting started. It's worth pointing out that Autodesk CFD, the software package we use and sell at D3 Technologies, is well suited for those who are new to CFD, or only use it occasionally. Autodesk CFD is what is commonly referred to as a general-purpose CFD package. It's not highly specialized to address a small niche of physics, but instead its purpose is to be more general and flexible, to address a wider range of applications. It's CAD neutral, meaning it's not picky about what design software you use, but it is designed to feel like a CAD system, as its intended user includes designers and engineers who use CAD frequently. In fact, this is true for the Autodesk Simulation products in general. What makes Autodesk Simulation different? Who uses Autodesk Simulation? The names you see on screen are makers of some good simulation tools. In fact, they're great. We at Autodesk and D3 Technologies don't see ourselves in direct competition with these products. In many instances, Autodesk products live in harmony with these other software packages, even within the same company, because they serve different purposes. Let me explain. Note the triangle graphic on screen. This triangle represents the entire community of engineers and designers. Traditionally, highly educated and highly specialized individuals, represented by the top portion of the triangle, have been relied upon to perform CFD and FEA analysis. These individuals are typically career analysts. They're expensive people who use expensive tools. This type of analysis is often done at the end of a design cycle for validation purposes. Autodesk Simulation is part of a newer approach to simulation, sometimes called upfront simulation. It's for the everyday engineer or designer. These individuals often wear many hats, and running analysis software may only be a part-time role. They need results early in the design process to help them make more informed decisions while the product is still in development. For this reason, they need the tool to be easy to learn and easy to use. Autodesk Simulation serves these users. So how does CFD work? Let's start by breaking this up into 5 simple components. Start with the input. We take some defined geometry, which is our CAD model. We define what that geometry is made of, and we identify areas on the geometry where fluid or heat enter and exit the model. We call those inlets and outlets boundary conditions. We feed all this input into a solver, which in turn spits out results. You may have heard terms like pre-processing, which means the stuff at the front end, the setup, or post-processing, which is the part where we process the results and dig out useful information. In the early days of CFD, these tasks, pre-processing, solving, and post-processing, were all handled by different software products. Some products still operate this way. It's getting more common now to see all of these functions rolled into a single interface, as is the case with Autodesk CFD, except for the geometry itself. Typically, the geometry is generated by a CAD system that is purpose-built for this task, and then that geometry is imported by the CFD interface. Autodesk CFD works in this way too. The geometry is typically defined by 3D solid CAD models, or BIM models. These represent the real-world solid objects, and fluid contained within them, or fluid that exists around them. This is where the CFD process begins. It's where the first decisions need to be made about the analysis. By deciding what geometry to include, we are defining the scope of our calculation. We are defining the limits of the calculation. We would not, of course, try to simulate the physics of the entire universe in order to predict the airflow in one room. The computer resources needed to simulate the entire universe would be immense, and defining the inputs of such a model is simply impractical. So we define limits. What small part of the universe is really needed in order to accurately model the behavior of our design? That will vary from analysis to analysis and depends on how many assumptions we're comfortable making, and how much time and energy we're willing to invest in getting the results. For example, when studying the behavior of our room, it's not necessary for us to model the entire building, as long as we're comfortable assuming our cooling air is entering at a certain temperature, and we're comfortable assuming a rate of heat transfer through the walls and windows. So all we need for geometry is the room itself, and any contents that will have a significant impact on the airflow. This does not mean that CFD is limited to small-scale problems. Physical size is not typically a limitation at all. Detail is what costs time and resources. Useful models of large-scale problems can be solved more easily when unnecessary geometric detail is omitted. For example, if we wanted to study the flow and thermal characteristics of a data center, we absolutely can, and this is a common CFD application. However, our room scale model will not include the screws holding up our light fixtures. It won't include the heatsink fins in our blade server. It won't model the server cooling fans spinning and the turbulent structures they generate. Instead, we'll make some assumptions about how much heat the entire server rack emits and the average velocity of its exhausted cooling air. This would be enough information for us to make decisions about our server layout and the location and power of its cooling units. We can model the blade server in detail too, but we would only do that if we were designing a blade server. By limiting the scope of the model to the individual server, we can afford to include much more detail, such as our board, components, and heat sinks. We probably still wouldn't model the cooling fan spinning. There are simpler ways to model the effect of the spinning fan. The fan itself is a pretty complex CFD problem, and we can absolutely solve it, but the model is probably going to be limited to the fan and maybe some of the geometry near its inlet and outlet that would affect its performance. But again, we'd only be doing this if we were designing the fan. So the geometry decisions depend on what we are designing. The level of detail is always a trade-off between realism and the cost of the analysis. The effects of the smaller details may be less consequential than you think. Highly simplified geometry is often employed to compare one design candidate to another, especially earlier in the design process when that detail is not developed yet. There are scale limits, of course, and it comes down to the equations that are employed by the software in its models. Autodesk CFD uses the Navier-Stokes equations, a common choice for general-purpose solvers. The physics that can be represented using Navier-Stokes cover a wide range of physical scales, but at some point models can get too small or too large. The dominant physical effects just aren't accounted for. Turbulence and boundary layers in microfluidic applications would not be well represented by Navier-Stokes. A climate model of the entire planet? While you could think of it as a CFD problem, it's not the type of problem we will be solving with a general-purpose engineering software application. The bottom line, if you're unsure whether your application is appropriate for your solver, look at the governing equations your solver uses and determine if those are appropriate for the physics you're trying to simulate. For most manufacturers, Navier-Stokes is going to fit. Boundary conditions are another essential piece of input for a CFD analysis. Once we've decided what geometry to include in the analysis, we've decided on what's called a domain. The domain is just the chunk of reality that we're simulating. Let's take this lobby, for example. We've chosen the external walls, some internal walls, a mezzanine, and some of the contents as our input geometry. This is our domain. At the external walls, we find the boundaries of our domain. Beyond the boundaries, we are not modeling physics, but assuming what is occurring. It's on these boundaries that we place our boundary conditions. In this example, we'd place an inlet and outlet boundary condition on our makeup air supply duct and exhaust ducts. This isn't necessarily where the ducts end in real life, it's just where we've chosen to cut it off, at the domain boundary. We'd specify conditions such as velocity, mass flow rate, pressure, and temperature. It depends on what we know about the real-world problem. What information do we have available? Or what assumptions do we want to make? Heat is also added or removed from buildings via convection to the outside air and radiation to or from the surrounding environment. These effects are often simplified with boundary conditions, using coefficients to remove, or in some cases add, heat, which are calculated based on assumed environmental conditions, like external air temperature and velocity. This would be done instead of actually modeling that surrounding air. When the effects are not simple enough to replace with boundary conditions, the physics will actually be modeled. Sometimes boundary conditions are not actually on the domain boundaries. Sometimes they're within it. In the case of our lobby, the human occupants are heat sources, so we specify a volume heat generation. Often we take advantage of special materials called devices. These are a kind of combination of materials and boundary conditions. We assign them to volumes-like materials, but they affect the model like boundary conditions. In our lobby, we have a rooftop AC unit that moves the air in our ducts, but also conditions it by removing heat and moisture. In real life, this is a complex piece of machinery with many moving parts. These machines are complex airflow and thermal analysis problems in of themselves, but we aren't designing air conditioners, so we're not going to include all of its real-life complexity. We want its effects. So the geometry of this unit can be a simple cuboid shape, but it behaves like the AC unit, with a number of options to define its performance, such as setting set points for air temperature and humidity. In the CFD model, this volume will generate momentum in the fluid and remove heat and moisture. This is just one example of a device. There are many other examples of heat exchangers, fans, pumps, and blowers that we can simplify in this way. Now the really fun stuff, the solver. This is where the magic happens, or should I say the math happens. It's more or less magic to mortals, though. You've got your continuity equation, and your momentum equations for x, y, and z. And of course, our old friend, the energy equation. You know that one, right? And then there's other stuff if you get into more specific physics, like humidity or joule heating. You taking notes? Good. Oh wait, you'll need the variable definitions. You getting all this? Yeah, me neither. Here's the thing. We have CFD software, so we don't need to do this stuff. I've suffered through some theoretical CFD classes, and this stuff is hard. I only passed them because half the class was applying the theory with software. For real-world problems, CFD is effectively impossible to do by hand. Only the simplest of problems should be attempted by hand in an academic setting. A solid understanding of fluid mechanics is going to help you, but being able to apply partial differential equations is not. I'll try and relate my understanding of the approach in simple terms. Solving a CFD problem is an attempt to find values for all physical variables, everywhere in the domain, that satisfy physical laws. Essentially, mass is conserved. Mass does not appear or disappear. If the mass in the domain changes, it must be because it entered or exited through a boundary condition. Changes in momentum at any point in the fluid domain must be accounted for in the forces acting on the fluid. Energy is conserved. Energy changes in the domain must be accounted for in the form of heat entering or leaving the system, or work being done. Solving these nonlinear equations is an iterative process. There are many variables involved, and they are dependent on each other. There are too many unknowns to find a single explicit answer. So the solution is dialed in to a point where error is acceptable. This involves initial guesses on physical values at the beginning of the analysis and assessment of the resulting physical values after the analysis to determine if they adhere to physical laws. Results of one iteration serve as input into successive iterations, the goal being to reduce the error between the actual result and a physically balanced result. It can take hundreds or thousands of iterations to arrive at a converged result. Depending on the size and detail of the model and the physics being simulated, this may be done for multiple variables at millions of points in the domain. This is why CFD is pretty much impossible to do by hand, and even still a challenge for modern computers. Analyses can take under an hour, but it's not uncommon for solve times to take multiple hours. Solve times that take days are not as common. Typically, there are multiple options when it comes to solving. You may be able to send the analysis task to another dedicated workstation or cloud resources on off-site data centers. Autodesk CFD includes both of these options. So, what do we get out of the solver? CFD simulates the movement of the fluids and the heat that is carried away by the fluids as they interact with our solid surfaces. CFD shows us what we can't see in a test, like the velocity of the fluid throughout the flow domain. This can be shown in a number of ways, but most commonly we view 2D slice planes. Color gradients are utilized to visually indicate local velocity magnitudes. At a glance, anyone can see where the fastest air is moving. We can also see the direction of the fluid flow at any point in the domain. Vector arrows can be shown on the cut planes and are incredibly helpful for showing the dominant flow path or areas of recirculation and stagnation. Of course, we're interested in temperatures. CFD can give us those temperatures. They're shown visually in a number of ways, typically with a color gradient. each color representing a magnitude of temperature. The actual magnitudes can also be measured and displayed at any point in the domain. Sure, it's easy enough to measure temperatures in real life with sensors or cameras, but that information is not available until we have built something. Remember, this is a virtual test. With CFD, we can have this information available before any materials or equipment have been ordered. But we get more than that. With CFD, we can begin to understand why we're getting these temperatures, because we also see the air moving. CFD is commonly associated with streamlines or trace lines. This is the spaghetti you see flowing through the operating room here. Think of it as the path that a particle would take through the flow domain. This is one of the ways recirculation or stagnation zones can be identified in CFD. Notice how in this case they are also colored, indicating the velocity of that theoretical particle at that point in the path. Visual results like this are extremely valuable for conveying information to other stakeholders in the design, such as customers, vendors, or contractors. Not everyone is good at comprehending the performance of a design by looking at numbers on a spreadsheet. Not everyone has a thorough understanding of fluid dynamics and heat transfer, but can understand that the airflow shown on the left image is more chaotic than the airflow shown on the right image. It's clear that in the improved design, air that has touched the staff does not head toward the table, but is pulled away. These two images alone would be more valuable to a decision maker than a 20-page report full of technical detail, although all that detail would be available to back up these results. Imagery like this is also commonly used as a marketing tool. Placed on our website or in YouTube videos, they give our customers the impression that we are sophisticated and on the cutting edge, and that we've done the research. Our CFD results are not the end of the story. What good is all this information if we don't act on it? The CFD process we looked at earlier should be cyclical. When we get our results, what do we do with them? Do we stop designing? Often, CFD, or simulation in general, is thought of something that happens at the end of a design to validate it, or it's used as a forensic tool to determine what went wrong with an existing space. These are valid use cases, but the simulation software industry is trying to get the word out that this technology is most effectively used throughout the design process. It should enable us to make better decisions at every decision point. So we know if we have a problem early on, and even more importantly, so we can quickly experiment with ideas that may prove to be great innovations, ideas that would be much more costly to explore with physical construction. The greatest potential in CFD is not in avoiding mistakes, but in finding our next great idea. Our CFD tool should allow us to easily iterate on the design we are testing and provide an environment to compare one design to another. In these images, captured in Autodesk CFD, you can see that visual results, numeric results, and results plotted in graphs can be compared side by side to quickly show which design changes improved performance and which did not. This is information that's valuable to us as the designers, but also to our managers and customers who need to approve these design changes. So in summary, CFD allows for virtual testing to preview the performance of a design before it's built. This helps to prevent costly rework. It leads to reduced project completion times. It allows you to bid faster and with more confidence, winning you more business. And it allows for rapid exploration of ideas and innovations that may be too risky or costly to experiment with in construction. Please contact us for more information. We can arrange a call with a specialist, such as myself, to discuss how D3 technologies can help you in your designs. Thank you so much for your time. We look forward to hearing from you.